Welcome back to Part C. We are picking up right where Part B ended. Let's continue. Section B. Here you choose any 3 questions. We'll work through all 5 so you can pick your strongest. Question 16. Part A is correlation. We are given 5 pairs of x and y values and asked for the correlation coefficient r, then a comment. The coefficient r measures how tightly the points hug a straight line. Close to plus or minus 1 means a strong line, close to 0 means a scatter. First find the means. X bar is 4 and y bar is 15. Using the deviations from these means, the sum of products SXY is minus 448, SXX is 224, and SYY is 896. Then R equals SXY over the square root of SXX times SYY. That is minus 448 over the square root of 224 times 896. This works out to exactly minus 1, a perfect negative correlation. Every point lies precisely on a falling line. Question 16, Part B. Now we build the regression line of y on x. Written y equals a plus bx. The slope b is SXY over SXX. That is minus 448 over 224, which is minus 2. The intercept a is y bar minus b times x bar. That is 15 minus 2 times 4, which is 23. So the regression line is y equals 23 minus 2x. To estimate x when y is 16, put 16 for y. 16 equals 23 minus 2x. Solving, 2x is 7, so x is 3.5. Question 17. Part A. The matrix A is 2, 2, 1, 3. Find its eigenvalues and eigenvectors. An eigenvector is a special direction that the matrix only stretches, never turns. The stretch factor is its eigenvalue. The eigenvalues come from the determinant of A minus lambda times the identity set to 0. That gives lambda squared minus 5 lambda plus 4 equals 0, which factors as lambda minus 1 times lambda minus 4. So the eigenvalues are 1 and 4. For lambda equal 1, solving A minus the identity times V equals 0 gives the eigenvector 2 minus 1. For lambda equal 4, the eigenvector is 1, 1. Question 17, Part B. Now we diagonalize. We build a matrix P whose columns are the eigenvectors, and a diagonal matrix D holding the matching eigenvalues. So P is 2, 1, minus 1, 1, and D is the diagonal 1 and 4. With this choice, P inverse AP equals D. For the inverse, the determinant of P is 2 times 1 minus 1 times minus 1, which is 3. So P inverse is 1/3 times the matrix 1 minus 1, 1, 2. You can check that P inverse times A times P really is diagonal, the diagonal 1 and 4. Question 17, Parts C and D. Here is the payoff of diagonalizing. Because A equals PDP inverse, any function of A acts only on the diagonal. G of A equals P times G of D times P inverse. For A to the 6th, we raise each eigenvalue to the 6th. 1 stays 1, and 4 to the 6th is 4096. Multiplying P, that diagonal, and P inverse gives A to the 6th as 1, 366, 2730, 1365, 2731. For f of A, we apply f to each eigenvalue. F of 1 is 2, f of 4 is minus 1. So f of A is P times the diagonal 2 and minus 1 times P inverse, which is 1, minus 2, minus 1, 0. Finally, for a real cube root B, take the cube roots of the eigenvalues, 1 and the cube root of 4, both real. Then B equals P times the diagonal 1 and cube root of 4 times P inverse, and B cubed returns A. Question 18, Part A. Find the locus of all points whose distances from 4, 0, and minus 4, 0 differ by 2. When the difference of the distances to 2 fixed points stays constant, the path traced is a hyperbola, and those 2 points are its foci. The foci are at plus and minus 4 on the x-axis, so C is 4. The constant difference is 2a, and here it is 2, so a is 1. For a hyperbola, b squared equals c squared minus a squared, that is 16 minus 1, which is 15. So the equation is x squared over 1 minus y squared over 15 equals 1. Question 18, Part B. Show that 4x squared plus 9y squared minus 48x plus 72y equals minus 144 is an ellipse. The plan is to complete the square in x and in y, then reach the standard form of a conic. Group the terms 4 times x squared minus 12x plus 9 times y squared plus 8y equals minus 144. Completing each square gives 4 times x minus 6 squared plus 9 times y plus 4 squared equals 144. Dividing by 144 gives x minus 6 squared over 36 plus y plus 4 squared over 16 equals 1. Both terms are positive with a plus sign, so it is an ellipse centered at 6 minus 4 with a equals 6 and b equals 4. Question 19, Parts A and B. We have two linked sequences u and v, and we define wn as vn minus un. To show w is geometric, we build the next term wn plus 1 and simplify until it is a constant times wn. wn plus 1 is vn plus 1 minus un plus 1, that is un plus 3, vn over 4 minus un plus 2, vn over 3. Over a common denominator of 12, this becomes Vn minus Un over 12, which is Wn over 12. So W is geometric with common ratio 1 over 12. The first term W1 is 1 minus 12, which is minus 11. So Wn equals minus 11 times 1 over 12 to the power n minus 1. Question 19, Parts C and D. First, convergence. A geometric sequence whose ratio has size less than 1 shrinks towards 0. Here the ratio is 1 over 12, whose size is less than 1, so Wn converges, and its limit is 0. Now monotonicity. Look at the step from one term to the next. Un plus 1 minus Un works out to 2/3 of Wn, and since Wn is negative, U is decreasing. Vn plus 1 minus Vn works out to minus Wn over 4, and since Wn is negative, this is positive, so V is increasing. So U falls, V rises, and their difference W tends to 0. Question 20, Parts A, B, and C. We study f of x equals 2 natural log x all over x. First, the domain. The natural logarithm only accepts positive inputs, so x must be greater than 0. The domain is 0 to infinity. Now the limits at the two ends. As x approaches 0 from the right, log x plunges to minus infinity while x is tiny and positive, so f goes to minus infinity. As x grows very large, the log grows far more slowly than x, so the fraction goes to 0. These limits give the asymptotes, a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. Question 20, Parts D and E. We differentiate f of x equals 2 log x over x. Using the quotient rule, the first derivative is 2 times 1 minus log x all over x squared. Differentiating again, the second derivative is 2 times 2 log x minus 3 all over x cubed. For variation, the sign is set by 1 minus log x. It is positive when x is below e and negative when x is above e, so f increases on 0 to e, decreases after e, with a maximum at e, 2 over e. For concavity, the sign follows 2 log x minus 3. The curve is concave down until x equals e to the 3/2, then concave up with an inflection at x equals e to the 3/2. Question 20, Parts F and G. For the intercepts, we set the function to 0 for the x-axis and check x equals 0 for the y-axis. The fraction is 0 only when its top is 0, so 2 log x equals 0, giving log x equals 0, so x equals 1. The curve meets the x-axis at 1, 0. Since x equals 0 is excluded from the domain, there is no y-intercept. Now the sketch. From minus infinity near the y-axis, the curve climbs, crosses the x-axis at 1, rises to its maximum at e 2 over e, then bends over and decays gently towards the x-axis as x grows. That completes the full study of the curve. A few reminders before your exam. Show every step. At this level, method marks matter most. Name the rule you are using, whether it's eigenvalues, the cross product, or completing the square. Check the special cases, signs, quadrants, domains, and units. And in Section B, choose the 3 questions you can finish completely. Wonderful work getting through an advanced level paper. You've now seen a clear method for every question here. Practice them in your own words, then try another past paper to build speed. With Inzira, you can learn, practice, and master. See you in the next one.